Hey, what's going on guys? Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms. And today we're going to talk in detail about the comparison between an array data structure and a linked list data structure. Now before we proceed ahead, I'm assuming you guys already know what is array data structure, what is linked list data structure. If you have any doubts, please check out this course, please check out this playlist. We've already covered both of these topics, both of these data structures extensively in detail. And this video is very important because here we are going to see the pros and cons of array data structure versus linked list data structure and try to understand which data structure is better in which scenarios. So what do I mean by these scenarios or conditions? Essentially what I'm trying to say is there is no such thing as one best data structure which can be suitable for all conditions. Every data structure is unique, be it linked list, be it array, be it stack, queue, or any other data structure. Each and every one of them have its own pros and cons, and they work efficiently in certain conditions while they don't work well in other conditions. So just note it down that no one particular data structure is the absolute best, and this is what we are going to try to find out in this tutorial. That's why this is a detailed video, and it is also important as to which data structure, that is whether array or linked list, is better in certain scenarios, and those scenarios, as you can see, are listed on the screen. So we are going to go through all these different points and conditions and compare the two data structures. If you're new to my channel, my name is Tanmay Sakpal and I do a lot of computer science and information technology video tutorials like computer programming, development, technology talks, and a lot more on this channel. So if that's something you're interested into, then definitely subscribe and turn on the notifications to get the latest updates and never miss out on such important topics. Now before we start off, a quick introduction for those who might have a little bit of doubt about these two data structures. What is an array? An array is a collection of elements of same type placed in contiguous memory locations. So this contiguous is a very important point or important keyword. We'll talk about it in a minute. And that can be individually referenced by using an index to a unique identifier. So when I say int ARR and I give it a static size, and let's say these are the elements. So in the memory, so imagine this is a computer memory, this is the RAM. In the memory, 4 blocks are assigned to these 4 individual elements in this array. And if you note the addresses, so these are fictitious addresses, these are not real addresses. I've just tried to denote them so that they sound or they look like they are contiguous. And when I say contiguous, it means right besides each other. Now this is an integer array, right? So we say int ARR4. They have unique indexes 0, 1, 2 and 3. That's how you can access individual elements. And they also obviously have addresses in the computer memory. This is the computer memory, you can see. Now you can see that they are right besides each other in the computer memory. But they are not right next to each other. They are right besides each other, which means that after hash 10, obviously we will have hash 11, 12, 13, right? But you can see hash 10 and then directly hash 14. So why is there a gap of 4? Now that is because a variable of int data type generally takes 4 bytes in the computer memory. It also takes 8 bytes depending upon your architecture. So I guess on a 64-bit architecture it takes 8 bytes. But let's assume that an integer variable or integer element will take 4 bytes. So the first variable or the first element in the array is at the index position 0 and it is having a value of 45. It's stored at the address of hash 10. Let's assume this is just address 10 and not hash. Usually addresses are, complex hexadecimal values. For simplicity purpose, let's assume it is 10. Obviously, the next element will be stored 4 bytes after hash 10. Since it is contiguous, which means it is right next to each other, obviously at address position hash 14, we will have the second element with the index of 1. The index positions obviously start with 0. So that's why at 1, we will have the second element. Again, if you add plus 4, we will get 18. So hash 18 is where we have the third element and plus 4 hash 22 is where we have the last element. So this is what contiguous memory allocation means. It means that right next to each other. Now if this was some other data type, if it was a char data type, so char takes 1 byte, right? 1 or 2 byte, I guess. Let's assume it is 1 byte. So in a char data type, what would have happened? The addresses would have been, let's say, hash 20. If the first address, that is the base address, is hash 20, the second address would be hash 21, third address would be hash 22, and depending upon how many number of elements we have, that's how the addresses will be. Okay, so this is what an array is in general, and this is how it looks like in a code format as well as in the memory. Now moving on to a linked list. A linked list is a collection of elements, again just like an array, which is also a collection of elements, and these elements in a linked list are also called as nodes that are not stored in contiguous memory locations. So this is one major difference, because in a linked list these nodes are scattered all across the computer memory. So in the computer memory diagram you can see first n1 and n2 are right besides each other, but n3 and n4 are basically somewhere in random positions in the computer memory. Now obviously, since it is a linked list, there has to be some link between these nodes, right? So the nodes are linked to each other using pointers. So pointers is not literally pointers, because then it will only be available in C and C++. A pointer is nothing but an entity that points to the next node. Now of course in C and C++ we use the concept of pointers, but in other general purpose programming languages we have different methodologies. So essentially this pointer is nothing but an entity that points to the next node so that there is a link. Now talking about this node, a node usually consists of two fields, namely data and next. So data is the actual value, data is also called as value, and the next is basically the next pointer pointing to the next node. Because as we just saw in the computer memory, the nodes are scattered all across the memory. They are not right besides each other. So we don't really know where a node will be created. It can be created at any random place. So we need to have some addresses stored, right? So n1 will store the address of n2, n2 will store the address of n3, and n3 will store the address of n4 in their next pointers. So that is what this next is all about. And data is nothing but the actual value. However, sometimes you also have a third field called as ID and name, and it is also used. So in our examples of linked list, whichever examples we've seen, singly linked list, doubly linked list and whatnot in this course, we always had key value as two fields and then the next pointer as the third field. Okay, so this is particularly for a singly linked list. If it was a doubly linked list, obviously we would have a previous pointer as well. And this is how the data structure visually looks like. So we have n1, which is created at memory address #100. Again, these addresses are fictitious, they are not real addresses, okay? So don't take them literally. This is just for representation purpose. So n1 is created at #100. It has the key of 1. So key is 1 in orange. 45 is the actual value stored inside this node. Value is also known as data. And then we have the next pointer which points to the next node. So n2 is created at address position 102. Over here in the memory also you can see. So 102 is stored inside the next pointer of n1 so that this link is made. Similarly, n2 is pointing to n3, n3 is pointing to n4, and in the next pointer of n4 we have null because n4 is not pointing to anything. We don't have anything over here, so a null is stored. Okay. Now we've already seen this in detail, so I'm not gonna get more into individual details. We want to compare the two different data structures based on certain criterias. So now let's move on to those criterias and try to compare which data structure is better in which certain scenarios. Okay, so the first parameter is the size of data structure. So the size in this case is how flexible is the size of the data structure. Now talking about arrays, in most general purpose programming languages, the simple arrays have to be declared and the size has to be given at compile time. So in C++ also you create an array and you give the size initially itself. So this is a very static way. And when I say static, it means that once you decide the size of the array, it will not change. So we can have an array of size 4. The values can change, keep on changing inside, but you cannot have one more extra element. So let's say right now we have 34, 56, 6 and 7. Let's say you want to store one more value of 75. You cannot create an extra space at the runtime when the program is running to store this 75. This is not possible in an array, right? So this is a major limitation when the size of the data structure is not flexible. Similarly, what if your data structure, that is the array, is not storing 4 values? So right now you can see we have 34, 56, 6 and 7. But in the program you realize that you don't really need 4 values, you only need 2 values. So in that scenario you can see that I have erased the 2 values. However, once you create an array of size 4, in the computer memory 4 blocks will be reserved for this array. So regardless of whether you want to store or whether you have any data in these last two elements or not, your array will always occupy 4 memory blocks, each for 1 int. And if you were to calculate, if we say 4 bytes for one element, we have 4 elements, right? So 4 into 4 equals to 16 bytes. So even though right now we have only 2 values in the array, still the array will always occupy 16 bytes in the memory. So this is not flexible, right? This is wastage of memory. So this is not efficient, right? This is wastage of 2 memory blocks and wastage of memory. Now I know this is just very trivial when it comes to 2 memory blocks, and in today's time we have a lot of memory storage, but this becomes a little inefficient when it comes to larger applications where a lot of flexibility of size of data structure is required. Now how does linked list fare in this comparison? So coming to the linked list has dynamic size in nature. When I say dynamic, what I mean is there is no fixed size of a linked list. Linked list can grow and shrink depending upon our requirement, depending upon the program's requirement at runtime. So right now you can see we have 4 nodes, but there is nothing written like we can only have 4 nodes. There is no rule. We didn't declare a linked list with size 4 like we did in array. So whenever you want to add a new node, what you can do, you can simply create that node object. So I'll create a new node object. I'll name it n5. Let's say the address that it is created at is #21. Okay. Let's say the key is 5. Data being stored is 65. And of course the next pointer for this is going to be null. Now simply what you have to do is, in the next pointer of n4, you have to store the address of n5, right? So this null has to be erased, and at the place of null, what do we want? We want the address of #21. So #21 would be added over here, and now this linking will be done. So n4 will start pointing to n5, and that's how you can see I have dynamically added one node. Now similarly, at any point in the program, let's assume that we don't really require n5. So you can also completely erase it out, right? So you can completely erase this out and make n4 again point to null. So you can see now I've dynamically shrinked the size. So this is one major benefit when it comes to the flexibility of size of data structure. So the size in linked list can grow and shrink depending upon the requirements. The size of array data structure cannot grow and shrink depending upon the requirements. So this is where linked list wins. Let's see the next criteria of comparison. Okay, so the next criteria of comparison is data access, read and update. So of course, in the array and linked list, we have multiple elements stored. In an array, our example is an integer array. In a linked list, it is a node which is storing integer data only. So the 34, 56, 6 and 1 are all integer values. Then we also have a key and the next pointer. So we have extra information per node. But now, whenever you want to access one particular element inside the array, how do you do it? What do we want to find out is the cost. So when I say cost, it means the time complexity. Now, if you don't know what is time complexity, what is space complexity, we have individually discussed these two topics in very detail. Those are absolutely important. Do check them out. But in general, time complexity is nothing but the time required to perform a particular operation. So in this case, the operation is data access and data read, which is pretty much one and the same thing. So when you access one particular element in the array, you are basically reading it, right? So data access and read is pretty much the same. And once you access that element, let's assume you want to update it. So again, after that, after accessing, you also can update it then and there. Hence the cost is obviously going to be the same for access, read and update. That's why I've put them and clubbed them together. So this is the criteria that we want to find out. That is, we want to find out which data structure is efficient when it comes to data access, read and update. Okay. Now talking about arrays, one advantage of array data structure is that we have random access availability. So the feature and functionality of random access is available. So when I say random access, in the array, you can access any element directly. What do I mean by this? So when you create an array, let's say ARR of 4, what happens is this ARR array basically points to the base address of the first element. So the first element is at index position 0. The base address of this is #10. So this array is pointing to this particular element. Now, if you have any general purpose programming language knowledge and you've seen the concept of arrays, whenever you want to access one particular element, let's say I want to access this last element, what do? I simply say ARR of 3, and let's say if I want to update it, I'll say ARR of 3 equals to 75. So what happens? Directly we jump to this location and we make the certain update. We make 7 as 75 and the updation is done. So you don't really have to traverse from index position 0 to 1 to 2 and to 3, right? You can directly use the index position to access the element in the array data structure. So this is called random access, okay? So random access is nothing but direct access of individual elements in a data structure, and that is possible in arrays. Now if you are wondering how this happens, as I mentioned, the array, since it is an integer array, knows the information of the base address. When I say base address, it means the address of the first element in the array. So it knows the address of the base element, which is hash 10. Now we've already known that in array elements are stored in contiguous memory allocations. So that means the next address obviously is going to be at address hash 14, and that is because it is an integer array. We just said that let's assume int data type to take 4 bytes. Now depending upon what system it is, it might be 8 bytes also, but we are assuming it is 4 bytes. So if you want to access the last element, that is index position 3, you can do it simply by using a formula which is given by base address plus this index position into the size in bytes of that particular data type. We know obviously integer array will store all integer values only. So a array data structure will store elements of the same data type. So over here it is int, which takes 4 bytes. So here size of one element is what we want to find out. Now if you substitute all the values, as I mentioned, the base address is always known in the array, which is hash 10. So it is 10 plus what is index position that we want to find out? We want to access index position 3. So it is 3 into what is the size of one element, that is one individual element. It is an integer type which is taking 4 bytes. So 3 into 4. Now if you calculate it, it is 3 4s are 12. 12 plus 10, it would be 22. And this, my friends, is the exact address of the last element in the array. So this is how when you say ARR of 3 and when you want to update it to 75, what is happening at the backend is this formula is applied and then the address is found out and the value is accessed at that address, and then you make the updation. So 7 is made to 75. But behind the scenes, this is what is happening. Okay. So you can see data access and read is pretty fast in an array. And the cost of data access, read and update in an array is termed as constant time. So when I say constant time, O of n equals to 1. We've already talked about different types of complexities, and the reason why it is constant time is it will take the same amount of time to access 2, it will take the same amount of time to access 1, and let's say your array has n elements, the nth element also will be accessed in the same amount of time that will take to access the first element, because it is a simple formula. You don't have to traverse the entire array, right? You don't have to use a loop to go from one element to other and to the next. That would take a lot of time. That would be linear time, right? And that's what is going to happen in linked list. So we'll come there. But in array, as I mentioned, since random access is possible, constant time is taken to access any element in the array, be it at the start or be it at the end. Hence, it is much more efficient when it comes to data access and update. Now, let's see what happens in a linked list when you have to access, read and update a particular data. Now, in a linked list, we know that the nodes are not in contiguous locations. They are not right next to each other. They are at random positions, and hence we require this link to figure out where the next node is. So you can see in n1's next pointer we have hash 34. Hash 34 is the address of n2, right? So that's why the linking is made. Now in a singly linked list, so this is an example of singly linked list, we have the front pointer, which is a separate pointer which points to the first node. So this is the first node. Now what happens if I want to access n4? Now in a linked list, as I mentioned, we do not have the facility and the feature of random access, which means I cannot use any particular formula to directly jump to n4, because obviously the addresses are random. These nodes are created at random memory addresses in the computer memory. So the only way to reach to n4 is to use this front pointer which is pointing to n1, then traverse to n2, then traverse to n3, and then traverse to n4. So you can see I have to loop through the entire linked list to access the last element. Now of course how the element will be accessed can be used by passing the key of this n4 node. And that is one major reason why in our entire tutorials we are using key field also, because we've decided that every node will have a unique key. So if I want to find out a node which has the key of 3, I know that n3 is the only node which will have key of 3 and no other node. So that is how I can also find out which node I want to access and update. So if I want to access a node with the key of 3, I will start from the front. I will check the key of n1. n1's key is 1. Is it matching with 3? No. Then I will move forward. I'll check the key of n2. I'll match it with 3. Is 2 equal to 3? No. Then I'll move forward. And when I get a match, then I will access node n3 and make the appropriate change. So let's say I want to change the data of 6 to 60. So once I access n3, I can make it to 60. Okay? But here, as I mentioned, random access is not possible. So what is possible is sequential access. So the only way you can access a data in linked list is by performing sequential access. Now this is a time consuming task, because just to access n4 you can see we had to start from n1, then go to n2, then go to n3, then go to n4. So in terms of time complexity, the big O notation for sequential access in a linked list is basically n. So n is nothing but linear time, which means that the time required to access nth node is directly proportional to the number of nodes we want to traverse, right? So let's say in the linked list we have 100 nodes and you want to access the 90th node. So you'll have to go from 1 to 2 to 3 to all the way till 90. So that would take time directly proportional to those 90 hops, right? Those 90 jumps. If your linked list was 1000 nodes long and you want to access 900 node, obviously it will take more time than a linked list which is of size 100 and you want to access 90th node. So it is directly proportional to n, right? That is the number of nodes in the linked list. So hence it is called linear time. So hence we can conclude that data access, read and update is much more faster in an array data structure in most scenarios compared to data access, read and update in linked list. Alright, so let's move on to the next criteria of comparison. So the next criteria of comparison is insertion and deletion of elements in the data structure. So which data structure is better when it comes to inserting and deleting elements from it? Is it array or linked list? Let's find out. Now of course we have three different places where insertion and deletion can happen. Insertion can happen at the beginning, which means at the very start. Insertion can happen at the end, which means at the end. So in linked list also at the start and at the end. And insertion and deletion can happen at any random nth position in between somewhere. Let's say you want to insert a node over here in between, or you want to insert a value in between over here. So that is also possible. Or you want to delete a middle value. You want to delete n3, which is a middle value in the linked list. So that is also possible. So these are three different scenarios for which different cost is required, and we'll figure that out in this video itself right now. And hence we have three different scenarios. Alright, let's start off with arrays. Okay, so in the array, let's assume we have created an integer array of size 4, but right now we only have 3 values inside the array. The fourth memory block is idle. And now we want to insert. Let's start off with insertion. We'll come to deletion later on. So when you want to insert at the beginning, you want to insert a new value. Let's say the new value is 75. You want to insert the 75 at index position 0. Now before you insert, what you have to do is you have to shift all these elements one places ahead, right? So 56 comes in 6th place, 6 comes at index position 3, and 34 goes over here. Only after shifting these values ahead, only then you can put 75 over here. So after doing that, now you can take this 75 and insert it at this place, right? But if you observe, you had to unnecessarily make these shifts happen first. So 34, 56 and 6 got shifted. Now imagine if you have an array of size 10 and you have 9 elements starting from 0 to index position 8, and then again you have to add one new element at the start. So again all those 9 elements first have to be shifted. So 9 hops has to be made. So inserting a new value in the array is a little time consuming, where an extra overhead is required to shift the existing elements one position ahead. So here the time required to make that shift happen is directly proportional to the size of the elements, right, in the array. So O of n over here is gonna be equal to n, which is linear time. So depending upon the number of elements in the array that you have, even if your array is size 10 and if you have 6 elements in it and you want to add a 7th element, those 6 elements have to shift one position each, which means 6 hops are required, and hence you can see that that activity is directly proportional to the number of elements in the array, not the size of the array, the number of elements existing in the array. So over here in our current scenario, we were having 3 elements and we wanted to add a 4th element 75. So first those 3 elements had to make 3 hops ahead to make space for the new element. And that is why insertion at the beginning takes linear time, because those n elements which are there in the array have to be shifted one place ahead. Okay? Alright, so I hope you've got this basic thing. Okay, so now let's talk about insertion and deletion at the end. So again, taking our very same example, initially let's say we have 34, 56 and 6, and we want to insert a new value 75. Now inserting and deleting at the end is very easy as long as you have memory space. Of course, if you don't have memory space, then that is a problem in array. But assume that we have memory space, you simply push that value at the end of the array. The reason is inserting at the end does not require any of the existing elements to be shifted. So there is no extra effort or extra overhead over here. So over here O of n, that is big O notation, is gonna be 1, which is constant time. Okay. Now talking about the last thing, that is insertion and deletion at random nth position. Let's say I want to insert one value at index position 1. Now again the same scenario happens, that when I want to push a new value, let's say I want to push 75 at this index position, which is index position 1. So obviously 56 and 6 has to go one indexes ahead, right? So again there is a overhead, and it is also going to be proportional to the number of elements which have to be shifted ahead. So generally again it is given by O of n equals to n, which is linear time. Now the reason why insertion and deletion at the beginning and insertion at random nth position has the same time complexity, it is because in a real world scenario obviously it is not going to be same. The time required to insert at a random nth position is going to be slightly less than the time required to insert at the beginning, because when you insert a new element in the beginning, all the elements have to be shifted ahead. But when you want to insert at this index position, you can see we did not have to move 34. We only had to move 56 and 6. So the time will be a little less, but it is still proportional to the number of elements after that particular index position. So when you consider n elements, of course it will be directly proportional to n only, and hence in a generalized way we depict O of n equals to n only, and that's why it is similar and same over here. Okay. Now we've discussed how to calculate time complexity in detail in the time complexity video, so if you're still confused, do watch that. But now let's talk about deletion. So this was all about insertion, and when it comes to deletion also the same scenario happens. So let's assume that you want to delete at the beginning. So when you want to delete 34, when you delete this 34, what happens is now you have to shift this 56 over here and this 6 over here, right? So again shifting has to be done because the first element is deleted. Deletion at the beginning means deleting the first value in the array. Once you delete the first element, obviously 56 becomes the first element, so it has to go at the index position 0 only to maintain the consistency. So that's why 56 will be shifted one position back, then 6 will be shifted one position back, and if you have n elements in the array, n hops will be required, and that's why again the O of n for deletion also is linear, that is n. Similarly, deletion at the end will not require any extra overhead. So again, let's say we have one value 75 over here and you want to delete it at the end, you simply go to that place and you delete it. Do you have to make any switches to the existing elements? No. So deletion at the end requires constant time. And lastly, again, deletion at random nth position also will require linear time, because if you delete 56, you'll have to switch or shift 6 over here. So every element ahead of 56, if you have n elements, they require n hops. So that's why it is also directly proportional to the number of elements ahead of that position, right? Hence it is also linear in nature, that is equal to n. So I hope I'm making sense. And now that we've completely computed the cost of insertion and deletion of elements in an array in these three different scenarios, let's see the cost of insertion and deletion of elements in a linked list. Now in a linked list, we already know that nodes can be dynamically added and dynamically deleted at any point, and the size is flexible, which means it can grow and shrink. So talking about insertion at the beginning, the only thing that you have to do is you simply have to take a new node. Let's say this is n5 with a key value of 5, which is created at address 10 and the data as 75. You have to take this new node, and what you have to do is you have to simply say this front will now start pointing to n5. n1's address, which is hash 12, has to be stored over here. So hash 12 will be stored over here. And when you do that, this linking will be made. So n5 will now start pointing to n1, and the new front value will now be n5. So front will start pointing to n5. You can see front is now pointing to n5. So over here we did not have to go through n1, n2, n3, n4, or we did not have to run through a loop. We simply had to take this node n5 and make this linking happen and make the front pointer point to this new node n5, because n5 now becomes the front of this linked list because we are inserting at the beginning. Now these three steps of creating n5, then n5 pointing to n1, and then the front pointing to this new node n5 will have constant time, right? So every time you want to add a new node, only these three steps will be required, which means the time required is always going to be constant. And that's why the big O notation over here is going to be 1, which is constant time. Similarly, when you want to delete also, the same process is followed, which means now you will simply say front will start pointing back to n1. So you erase this link, and then you can simply delete this node, and now n1 becomes the front. So every time you want to delete one node from the front, you simply have to make the front pointer point to the next node. So that is also going to take constant time, right? So you don't have to iterate through the entire list. You don't have to run any loops. So again, deletion at the beginning also takes constant time. So O of n is 1 for both insertion and deletion. Okay? Alright. Now let's talk about insertion and deletion at the end. Now this is where the traversal of the entire linked list is required. Now remember, in linked list, as we know, nodes are created at random positions. We can only access directly n1 using the front pointer. But since we want to insert a new node at the end, that is at this position, let's say this is n5 with the address of hash 75. Okay, let's say the value is 5 and the key is also 5. Of course, initially it will have null in the next pointer. And now what we want to do, we want to make n4 point to n5. n4 currently has null over here, but when you want to insert or delete at the end, let's talk about insert first. We will have to traverse till the end using the front pointer. So the front pointer right now is pointing to n1. You'll have to go over here, then you'll have to go over here, then you'll have to go over here, and when you reach the end, the last node obviously will have null in its next pointer. So that's where you stop the looping and you determine that now, okay, now you're at the end. But you can see you require 4 iterations because we had 4 nodes. Imagine if your linked list had 100 nodes. So you require 100 hops or 100 iterations to reach the end, starting from the front node. So over here, inserting a new node at the end is directly proportional to the size of the linked list, which is the number of nodes. So you can safely say O of n is equal to n, which is linear. Now when you talk about deletion at the end, again the same procedure has to be followed. You'll have to traverse till the end, right? You'll have to start from n1, go to n2, go to n3, go to n4, go to n5, and once you come at n5, you realize, okay, in the next pointer of n5 we have null, which means we've arrived at the last node. Then you can easily delete this out. So again, deletion also requires linear time, which is directly proportional to n, because you have to traverse, you cannot directly jump to the end. Alright. Now talking about insertion and deletion at random nth position, let's say you want to insert a new node in between. Again, you'll at least have to traverse till that point, right? So if you want to insert a new node between n2 and n3, you will have to start from n1, you'll have to go to n2, and then you can add a new node in between and make the linking happen. How the linking happens, we've discussed in linked list in detail, but right now what I'm trying to say is, when you want to insert or delete a node in a random position in between, again it is directly proportional to the linear time, which is n hops are required to reach that position. So let's say you have 1000 elements or 1000 nodes and you want to enter a new node at the 50th position, so you'll have to make 50 hops to reach that position, right? So that's why again O of n is directly proportional to n, and this n represents the hops required to reach that particular position. Okay, so again this is linear. So now if you compare both arrays and linked list, it is pretty much a tie. When it comes to insertion and deletion at the end, the array is much more efficient with constant time. When it comes to insertion and deletion at the beginning, seems like the node is efficient with constant time, and otherwise it is n and n, which is linear time. So it's pretty much a tie over here. And I hope you've got a good idea about insertion and deletion of elements with these both different data structures. Okay, so let's move on to the next parameter, next criteria. Okay, so the next criteria is related to memory requirement and memory usage and efficiency. So these are two separate terms and separate things, but I've clubbed them together because they are both related to memory and we'll understand them better when we take them or club them together. So let's talk about arrays when it comes to memory requirement. So over here we've declared a int array of size 4, and considering int data type to take 4 bytes, we can easily say that 4 elements in this array will take a total of 4 into 4, which is equal to 16 bytes. So we are able to store 4 elements in 16 bytes. Now let's take the similar scenario in linked list. Okay, so in a linked list, we are storing integer data only. You can see the value or the main data element is of integer type only. But along with that, in a node, we also have key, which is also integer data type. We also have one pointer. So extra things are required in one element of a node. We just said that int is gonna take 4 bytes. In a node n1, there are 2 elements, which is the key, which is 1, and which is the data, that is 34. So there are 2 integer elements, which means we already have 8 bytes. Plus we also have one pointer. Now pointer generally takes 4 bytes, I guess, and it takes 8 bytes on a 64-bit. I'm not pretty sure, but let's assume it takes 4 bytes. So 8 plus 4. So totally one node in this scenario is taking 12 bytes. So 4 nodes will take 12 into 4, which is 48 bytes. Okay, now clearly just by observing these two values, 16 bytes and 48 bytes, you can see that array is using much less memory to store the same data. You can see the same data is stored. We are storing integer data 34, 56, 6 and 7. In the nodes also we are storing 34, 56, 6 and let's assume this is 7. Okay, I made it 1, let's take it 7. But clearly storing the same integer values in a linked list, it is taking more data. So you might conclude that okay, arrays are much more better, right? But that is not true. That is because in array, the size of the array is fixed. And right now, since the array was having all the index positions filled with data, we could conclude that array is better than linked list. Now imagine if the array was of size 100. So ARR of 100. Okay. So 100 integer data type elements will require how much memory? So 4 into 100, right? So that would be 400 bytes. So let's say we create an array of size 100. However, in the array, we are only currently having 4 elements filled and rest of them are all blank. We created the array and we gave the static size in the start of the program because we didn't know how many number of elements we are going to store in array. So that's why we gave a large value, and generally that is what happens, right? So let's say initially we only have 34, 56, 6 and 7. Rest of all the 96 blocks are going to waste because in the computer memory obviously 400 bytes are only going to be used. And now if you compare this with the linked list, remember in linked list, depending upon the requirement the nodes are created. So now we have 4 values in the array, but the array size is 100. So that's why it is taking 400 bytes. But if you compare the linked list, we have 4 values in the linked list, that is 4 nodes, and we are taking only 48 bytes. So now the linked list is more efficient. So that's where memory usage and efficiency comes into picture. So now you can see linked list is faring better. So it all depends upon the situation. Another use case can be shown as, let's assume or let's imagine that the array is not of integer data type. Let's say you are creating a class. I'll show the class on the screen. Let's say you are creating a person class. It has name, which is a character array of size 10. It has age, which is an integer type, and it has salary. Let's assume also as integer type. So collectively when you create a person object, so person obj, the size of one obj object in the memory is 10 bytes of the character array name plus 4 bytes of age and plus 4 bytes of salary, which is going to be 18 bytes, right? But let's say you create an array of person obj. You can also create an array of objects, right? So let's say you say person obj, you say 100. So you're creating a person obj array of size 100. So that would require 18 bytes into 100 because 18 bytes is required for one object. When you create an array of object of size 100, so 18 into 100 we will have 18000 bytes. And imagine if you are only storing 3 elements or 3 person objects, which means you are only utilizing 18 into 3, which is 54 bytes. Okay. Now take the same scenario in the linked list side. You create 3 nodes, n1, n2 and n3 of person type. So n1 is not going to store integer, it is going to store a person object. So n1 already has one extra key which is taking 4 bytes plus this person object which we just concluded, which takes 18 bytes, so 18 bytes plus the pointer which takes 4 bytes. So what is the total? 26 bytes, right? So one node takes 26 bytes. So 3 nodes will take how many? They will take 78 bytes of memory when the application is running. Now compare it with the person obj which you gave a size of static 100. Now the reason why you gave a 100 size is because in the program you don't know how many number of objects will be added at runtime. So just to be on the safe side, you gave 100, which means in the memory you've blocked 1800 bytes of memory. But in reality, if you would have used a linked list, you would have only utilized 78 bytes when you create 3 nodes. So now you can see there is a considerable difference. 1800 is much more larger than 78. You're wasting a lot of memory when you create a person object array, which is an array of complex data type, which has a larger size. In that case, you are wasting a lot of memory if you don't know how many number of elements you're going to store for sure. So that's where linked list is now definitely leaps and bounds ahead when it comes to memory usage and efficiency. Okay. So ultimately, seeing all these scenarios, we can conclude that the memory requirement usually of 1 unit of element in a linked list is usually higher, which means one node over here was taking 12 bytes, one element in the integer array was taking only 4 bytes. But when it comes to a larger application, that is when it comes to memory usage and efficiency, since linked list can add and delete nodes dynamically at runtime, depending upon whether you need or not, you're not going to waste any kind of memory. In arrays, you can see that since we don't know how many number of elements are supposed to be added, if you give extra size, that size is wasted. If you give less size and let's say you want to store extra elements, then you'll have to recreate a new array with a larger size. So that's another problem. So I hope you've got an overall picture of memory requirement and memory usage. These are two separate terms and how they are applied in an array or in a linked list. So it's pretty much a tie over here, and as I mentioned again, it depends upon the application and depends upon the condition. If you want to store primitive data types and if you already know the number of elements that you want to store, you can go ahead with arrays. If you are working with complex data types and if you don't know how many number of elements are required at any given point in the program, then you are better off with linked list and you'll save a lot of memory. So again, depends upon the condition. Okay, so let's move on to the next criteria. The next criteria is pretty basic, which is ease of use. Now of course, ease of use has to be given hands down to arrays. Arrays are much more easier to use. When it comes to a linked list, it is a little tedious because you have to make these linkings yourself. When it comes to C and C++ programming, you're dealing with pointers and a lot of memory leaks can happen. And you have to write a lot of code to manage these linked lists. So hence, arrays are much more easier to use. You can directly create an array. You don't really have to write a separate class also when you want to utilize arrays. In linked list, you'll have to create your own class or use some other library for linked list. So ease of use is hands down given to arrays. Let's move on to the last criteria. The last criteria is searching methods. So when it comes to searching an array, you can have two different types. You have sequential search. You can also have binary search, and you can also do the mapping of indexes. So if you already know the index, you can directly go to that. So random access is also possible. But when it comes to linked list, you cannot do binary search. You can only do sequential search, which means you'll have to start from n1, you'll have to go to n2, you'll have to go to n3, and at every hop you'll have to check with the key, whichever key you want. So if you want a node with key value of 4, you'll have to compare key of n1, you'll have to compare key of n2, then n3, and keep on jumping till you find a node with the same key of 4. So that's why in searching, linked list has a clear drawback, which has only sequential search. Okay, please don't mind my handwriting. I always had a very bad handwriting, but yeah, you get the point, right? So these were the different conditions, these were the different criterias on which we can make a comparison between arrays and linked list, and ultimately we come to the same conclusion which I initially mentioned, that there is no such thing as one perfect data structure which can suit all different conditions. It is depending upon your requirement, depending upon the program conditions and the logic, that you have to select that appropriate data structure. Okay, so each and every data structure is unique and has its own pros and cons, and you have to select them accordingly. Okay, so that's it for this video, guys. I'm gonna conclude it over here. I know it was a little lengthy, but it was important, and a detailed video on the comparison between array and linked list data structure, which one is better in which conditions. I hope you've understood all the different parameters. If you like this video, if you understood it, please give this video a like. Let me know in the comments how this video was. If you have any queries, you can put them in the comments. Do share this video with your friends. This is an important one. And I'm gonna wrap this video over here. So thanks for watching. See you in the next one. Peace.